Welcome to the Deep Dive.
Glad to be here.
Today, we're really plunging into something pretty fundamental to the modern tech world.
We are indeed Python.
Exactly, the Python programming language. We've gathered, well, quite a stack of sources for this.
Yeah, comprehensive research docs, articles, detailed notes, the works.
And our mission really is to sift through all of this material, pull out the most important bits, the key insights.
Basically give you that well-informed shortcut, help you understand why Python is such a big deal right now.
And, you know, the sources hit you with a statistic right away that just, wow, it sets the stage.
Oh yeah, the TIOBE Index one from May 2025.
That's the one. Python hitting #1 isn't the whole story. It reached an evaluation of 25.35%.
Which sounds high, but the context is key. The sources emphasize this, put it over 15% ahead of C++, the next language down.
15%. That gap it's huge. But
Yeah.
here's the kicker. The sources point out this 25.35% share. It's the highest share achieved by any language in the TIOBE Index's entire history.
Wow, any language, ever.
With, okay, one specific, very early exception for Java when the index was, let's say, less comprehensive. But in the modern era, unprecedented.
So it's not just popular, it's historically record-breakingly dominant right now, based on that metric.
Exactly. Which leads us straight to the core question we want to explore today.
How did this happen? How did a language that, started almost as a side project?
Right, not initially conceived as this world beater.
How did it achieve this kind of dominance, set these records?
It's a fascinating journey. And the sources trace it back to the beginning, to its creator.
Guido van Rossum.
Yep. He started working on it back in December 1989.
And the first public release, that was February 20th, 1991.
And the name, Python, it's not what you might think.
No snakes involved. The sources have this great little origin story.
Go on.
Well, Guido was apparently reading scripts from Monty Python's Flying Circus.
The comedy group. Seriously.
Seriously. He wanted a name that was short, unique, maybe a bit mysterious, a bit fun.
So Python it was, as a tribute.
Exactly. A touch of humor right in its DNA.
I kind of love that. It fits the language's vibe somehow. The sources also dig up Guido's stated goals from way back in 1999.
Ah, yes. His vision for it.
He wanted an easy and intuitive, powerful open source.
Readable, almost like plain English.
And importantly, allow for really quick development times.
And looking back now, the sources make the point that, wow, he pretty much nailed it. Over 2 decades later, those initial goals perfectly describe why Python is so successful today.
It wasn't an overnight explosion, though. The sources track the milestones. Version 1.0 came out in 1994.
Then 2.0 in the year 2000, that one added some really key functions, stuff that became central to the language.
But then things got maybe a little messy.
Well, as it grew, some inconsistencies crept in, some repetitive ways to do things. The sources mention this led to a major effort.
Python 3.0,
Yeah.
released in 2008.
And the big idea there was cleanup. Streamlining the language, removing redundancy, making it more consistent.
Which meant, crucially, breaking backward compatibility with the Python 2 series.
A controversial move at the time, maybe, but the sources frame it as necessary for the long-term health and clarity of the language. A deliberate choice.
Yeah, sometimes you need that clean break.
Right.
Okay, so that's the backstory. But let's bring it back to the listener. Why should you care about Python? Maybe you're not a programmer.
And that's a fair question. But the sources argue that understanding Python is, well, fundamental in 2025, regardless of your specific role.
Doubt so.
Because its influence is everywhere. It's not just in the software itself, it's in the data that shapes major decisions. It's powering the AI you hear about constantly.
It's running the backends of websites you use every day.
It's automating tasks in countless industries. So whether you're prepping for something specific, trying to understand tech trends, or just curious.
Knowing about Python gives you a crucial piece of the puzzle.
Exactly. This deep dive isn't just about the technical details, the what. It's about the why. Why is it so versatile? Why so dominant? It's your shortcut to being genuinely informed about a truly foundational technology today.
All right, let's get into the why then. What are the core strengths? What makes Python, well, Python, according to our sources?
The absolute first thing everyone points to, and the sources hammer this home, is its simplicity and readability.
That reads like English goal Guido had.
Pretty much. The syntax is deliberately clean. And a huge part of that, the sources highlight, is the use of indentation.
Right, using white space to define code blocks instead of, say, curly braces like in C++ or Java.
Exactly. And while that might seem like a small thing, it forces a certain level of visual structure and consistency.
Making it easier to actually read and follow the logic.
Significantly easier, according to the sources. It enhances readability quite dramatically. It connects directly back to Guido's goal of making code understandable.
And that's not just about looking nice. Easier code means.
It means developers can focus more on solving the problem, less on fighting the syntax. It makes teamwork easier, reading each other's code. It generally speeds up the development process.
So readability is a practical advantage.
A huge one. Another massive strength. It's free and open source.
Free as in no cost to download and use.
Precisely. That removes a major barrier to entry. Anyone, anywhere can start learning and using Python without needing expensive software licenses.
And the open source part.
That means its source code is publicly available. Anyone can look at it, suggest improvements, contribute fixes. It fosters this global, collaborative development model.
So it's constantly being improved by a worldwide community.
Exactly. Thousands of developers, users, testers are involved. This ensures it stays robust, relevant, and keeps evolving based on real-world needs. It's a powerful model.
Tied into that, the sources mention its versatility. It's not just for one thing.
Right. It supports multiple programming styles or paradigms. You can write procedural code, sort of step-by-step instructions. You can use object-oriented programming, organizing code around objects, or even functional programming approaches.
So you can pick the style that fits the problem best.
Yes, it gives developers flexibility, and that flexibility shows up in where it's used. The list in the sources is extensive.
Right.
Web development backends, obviously, data science, machine learning, huge areas, general software development, scripting, automation, testing.
Even game development gets a mention.
It really is adaptable. Learning Python opens doors in so many different fields. It's a truly versatile skill.
And supporting all this is the community. The sources mention millions of developers.
Millions. And that huge, active community is an incredible resource. If you run into a problem, chances are someone else already has.
And there's a solution posted online somewhere, Stack Overflow, forums, etc.
Absolutely. That collective knowledge base speeds up learning and problem solving immensely. It's a constant feedback loop of questions, answers, and shared knowledge.
Which leads us nicely into maybe its biggest strength, the libraries.
Oh, the ecosystem. It's phenomenal. The sources mention Python comes with a solid standard library built in, but then there are over 137,000 additional external packages you can easily install.
137,000. What exactly are these libraries and packages?
Think of them as pre-written code modules for specific tasks. Need to do complex math? There's a library. Need to analyze data? Library. Build a website. Frameworks, which are like bigger libraries.
You don't have to write everything from scratch.
Not even close. You leverage the work of thousands of other developers. It drastically speeds up development. Instead of spending weeks writing code to, say, read a specific file format, you just import a library that does it in a couple of lines.
The sources give tons of examples for data science.
NumPy is fundamental. It provides high-performance arrays and mathematical functions, absolutely essential for any kind of numerical work.
And pandas.
Pandas is the king for data manipulation and analysis. It introduces the data frame, this powerful table-like structure, making it much easier to clean, transform, filter, and analyze structured data. Honestly, data science in Python often starts with pandas.
Then Matplotlib for making charts and graphs.
Yep, for visualizing your data, which is crucial for understanding it and communicating findings.
Okay, and for AI and machine learning, Python's huge there.
Dominant, really. And again, it's the libraries. Scikit-learn provides a whole suite of classic machine learning algorithms, classification, regression, clustering in an easy-to-use package.
Great for getting started or standard tasks.
Definitely. Then you have the heavy hitters for deep learning, the neural networks, TensorFlow, developed by Google, and Keras, which often runs on top of it.
And PyTorch is another big one.
Yes, PyTorch is known for its flexibility, especially popular in research. These libraries provide the tools to build incredibly complex AI models.
Python's role in AML seems almost entirely built on these specific libraries.
Largely, yes. Python provides the easy-to-use front end, while these libraries handle the intense computations, often using optimized C or C++ code behind the scenes.
What about building websites?
Two main frameworks get highlighted. Flask is described as a micro-framework. Lightweight, minimal, gives you the basics and lets you choose the rest. Great for smaller projects or APIs.
And the alternative.
Django. That's the batteries included, full stack framework. It comes with a lot more built-in components, database tools, admin interfaces, templating designed for rapid development of larger, feature-rich applications.
So options depending on the scale and complexity.
Exactly. Then there's automation. Libraries like Selenium let you control a web browser programmatically.
Useful for testing websites or scraping data.
Right. And PyAutoGI lets you automate desktop tasks by controlling the mouse and keyboard. Plus, Python itself is just a great language for writing scripts to automate everyday repetitive tasks.
Cybersecurity gets mentioned too, with Scapy for network stuff.
And even game development with Pygame for 2D games.
It's just an incredible breadth of capability, all accessible through these add-on libraries.
That's the key. The core language is simple, but the ecosystem makes it immensely powerful and versatile.
And the sources point out a kind of synergy here, right? How these strengths feed each other.
Absolutely, it's a positive feedback loop. Simplicity attracts users. More users mean a bigger community.
A bigger community contributes more to open source, builds more libraries.
Which makes Python more powerful and versatile, attracting even more users for complex tasks.
So ease of use leads to community, community leads to libraries, libraries lead to power, power leads to more users.
It's this self-reinforcing cycle, and the sources argue this is a major reason for Python's continuous growth and its current top ranking. It's the whole package working together.
Makes sense. But, okay, nothing's perfect. We need to look at the other side of the coin. What are Python's limitations or drawbacks according to the sources?
The number one limitation mentioned almost universally is execution speed.
It runs slower than some other languages.
Generally, yes. Compared to languages like C or C++ that are compiled directly into machine instructions before running, Python takes a different approach.
It's interpreted. What does that mean in practice?
It means there's an interpreter program that reads your Python code line by line and executes it on the fly. This adds an extra layer of translation during runtime. Compiled languages do that translation step up front.
So that extra step makes it slower.
For CPU-intensive operations, potentially yes. The sources mention it can be significantly slower, maybe even up to 100 times slower than optimized C code in some specific compute-heavy benchmarks.
100 times? That sounds bad.
It does, but the sources add crucial context. First, that kind of difference is rare in typical applications. Second, and this is key, many of the performance-critical libraries Python uses.
Like NumPy or parts of TensorFlow.
Exactly. Those libraries often have their core speed-sensitive algorithms written in C or C++R. So you're using Python's easy syntax to call super fast C code.
So you get the best of both worlds sometimes. Python for development speed, C for execution speed where it matters.
Precisely. It's a fundamental trade-off. Python prioritizes developer productivity, readability, and faster development time. The cost can sometimes be slower execution time compared to lower-level languages. Understanding this trade-off is crucial.
So it's about choosing the right tool, especially if raw speed is the absolute top priority.
Right. Another point raised is memory consumption. Python can use more memory than some other languages.
Any idea why?
The sources link it to features that make development easier, like dynamic typing and automatic memory management, garbage collection. These systems provide flexibility, but aren't always the most memory frugal.
And that matters more when you're dealing with huge amounts of data.
Exactly. In AI, machine learning, big data analysis fields where Python is popular, you might be processing gigabytes or terabytes of data. High memory usage can become a constraint there. The sources also note it's possible to have memory leaks if you're not careful, especially in programs that run for a long time. Tools exist to monitor usage, though.
Okay. What about mobile apps? Can you build an iPhone or Android app directly with Python?
Generally, no, not natively. The sources are clear on this. Android primarily uses Java or Kotlin. iOS uses Swift or Objective-C. Python isn't directly supported out of the box.
But aren't there tools that let you?
There are frameworks, like Kivy or Beware, that try to package Python for mobile. But the sources indicate this adds complexity, and the resulting apps might not feel truly native on the device.
And you might still run into platform-specific hurdles for publishing, like needing a Mac for iOS apps.
Exactly. So while technically possible with these extra layers, it's often not the most straightforward or preferred route compared to using the native languages.
Got it. Any other technical drawbacks mentioned?
Briefly, yes. The Global Interpreter Lock, or GIL, in the standard CPython implementation, it's a bit technical.
Give us the gist.
Essentially, for tasks that are heavy on CPU calculations, not waiting for networks or files, the GIL can prevent multiple threads from running Python code truly in parallel on different CPU cores. It can limit the speedup you get from multi-core processors for certain types of Python workloads.
Okay, a potential bottleneck for some parallel tasks.
Yes. Also, dynamic typing, while flexible, means some type-related errors might only show up when you run the program, not when you write it, unlike statically typed languages. Packaging applications for distribution can sometimes be a bit complex due to different tools and methods, and the automatic garbage collection, while helpful, can sometimes cause brief, unpredictable pauses or contribute to memory issues in complex, long-running systems if not carefully managed.
Listening to these drawbacks, it really sounds like many of them are direct consequences of the features that make Python popular in the first place.
That's exactly the point the sources make. They literally say the disadvantages are often the other face of its advantages.
So interpreted execution makes it flexible but slower. Dynamic typing makes it easy to write but can lead to runtime errors. Automatic memory management is convenient but can use more memory.
It's all about the design choices and the trade-offs involved. Python was designed to optimize for developer happiness and speed of development. Raw execution speed or absolute memory efficiency weren't the primary goals, though they matter.
But the community isn't just ignoring these limitations, right? The sources mention efforts to mitigate them.
Definitely not ignoring them. We already talked about the main strategy, using Python as a glue to call high-performance libraries written in C or C++. That handles a lot of the speed issues in data science and ML.
But beyond that, are there ways to make Python itself faster?
Yes. The sources highlight projects like PyPy. It's an alternative Python interpreter that uses techniques like just-in-time JIT compilation. For many types of long-running programs, PyPy can offer significant speedups over standard CPython.
Interesting. And Python.
Python is different. It lets you write code that looks like Python but adds static type declarations. This Python code can then be compiled directly into very fast C extensions, so you can speed up critical bottlenecks in your Python code by rewriting just those parts in Python.
So there are active efforts to improve performance.
Absolutely. These projects, plus ongoing improvements within CPython itself, show a commitment to addressing the speed issue. It's about leveraging Python's strengths while finding ways to work around its main weakness where necessary.
Okay, let's shift gears slightly. For someone new to this, how does Python code actually look? What are the fundamental pieces, the building blocks, as described in the sources?
The sources start with the basics: variables and data types. Variables are just names you assign to store data, like my variable equals 10.
And they're case sensitive. My variable is different from my variable.
Correct. And crucially, Python uses dynamic typing. You don't declare the type of data a variable will hold up front.
So the type is figured out when you assign the value.
Exactly. You can assign an integer, then later assign a string to the same variable name, x, then x equals hello. This is flexible, but means you need to keep track of what type of data is currently stored.
What are the main data types the sources cover?
Well, you have your numeric types, integers, floating point numbers, float for decimals, and even complex numbers. Strings. Strings, they're sequences of characters. Python doesn't have a separate type for a single character. It's just a string of length 1.
Then you have collections. Things like lists.
Right. Lists are ordered collections of items enclosed in square brackets. They are mutable, meaning you can change them after creation, add items, remove items, change items. They can hold different data types, too. Very flexible.
And tuples. They sound similar.
Tuples, enclosed in parentheses, are also ordered collections, but they are immutable. Once you create a tuple, you can't change its contents.
Why use an immutable one?
Useful for things that shouldn't change, like coordinates, XY, or database records. Because they're immutable, they can also be used as keys in dictionaries, unlike lists.
Dictionaries. Those are key value pairs.
Exactly, enclosed in curly braces. Like a real dictionary, you have a unique key, say a word, that maps to a value, its definition. Super useful for representing structured data, and lookups by key are very fast. The sources note they are ordered by insertion sequence from Python 3.7 onwards.
Okay, we also have booleans.
Yep, the bool type, which is just true or false. Essential for logic and conditions.
And sets.
Sets, set, also using curly braces, but only storing keys, no values. They are unordered collections of unique elements. Great for removing duplicates from a list or checking if an item exists in a collection quickly. They're mutable.
Is there an immutable set?
Yes, frozen set. Same idea, unique, unordered elements, but immutable, so they can be used where immutability is needed, like inside another set or as dictionary keys.
So lots of ways to store different kinds of data. How do you control the flow of the program? Make decisions?
That's where conditional statements come in. If, elif, which means else if, and else.
Standard programming logic.
Pretty much. If some condition is true, execute this block of code. Elif another condition is true, execute that block. Else, if none of the above were true, execute this final block. And again, Python uses indentation to show which lines belong to which block.
And for repetition.
Loops. There are two main types, for loops and while loops.
For loops are typically for iterating over collections.
Exactly. For item in my list, we'll execute the loop body once for each item in my list. You can loop over lists, tuples, strings, dictionary keys, etc. Very common.
And while loops.
While loops keep executing as long as the specified condition remains true. While count 10. Useful when you don't know exactly how many times you need to loop beforehand.
The sources also mention loop control things. Break and continue.
Right. Break exits the loop entirely, immediately. Continues, skips the rest of the current iteration, and jumps to the start of the next one. Useful for controlling loop flow based on conditions inside the loop.
And reusable code blocks. Functions.
Functions are key for organization and reusability. You define a block of code with the def keyword, give it a name, and then you can call that function whenever you need to execute that code.
You can pass data into them.
Yes, using parameters or arguments. And functions can return a value back to the caller using the return statement. This avoids repeating the same code snippets over and over.
Python also strongly supports object-oriented programming, or OOP.
Yes. OOP is a major paradigm available in Python. It's about structuring your code around objects, which bundle together data, attributes, and behavior methods.
So you define a class.
Which acts as a blueprint. For example, a class dog blueprint.
And then you create specific objects or instances from that blueprint.
Exactly. My dog. Inderkaway. Each object has its own attributes, like mydog.name, Fido. The sources mention the special init method, the constructor, which runs automatically when you create an object, used to set up its initial state.
And self. That keyword pops up a lot in OOP examples.
Self is used inside the class definition to refer to the specific instance of the object being worked on. Self.name refers to the name attribute of that particular dog object.
OOP also involves concepts like inheritance.
Right. A new class, child, can inherit properties and methods from an existing class, parent, like a poodle class inheriting from the dog class. Promotes code reuse. The sources also touch on encapsulation, hiding internal details, and polymorphism, objects responding differently to the same method call.
File handling seems like a common need. How does Python handle that?
Pretty elegantly. There's a built-in open function to open files. You specify the file path and a mode like R for read, WVO for write, which overwrites, A for append.
Lots of modes mentioned in the sources, including binary ones.
Yes, RB, WB, AB for binary data, and modes like R plus Ixiobo plus A plus for combined reading and writing. Once opened, you can read data using methods like .rid, .readline or .readlines, or write using .write.
And closing the file is important.
Crucial, you need to call .close to save changes and free up system resources. But the preferred way, highlighted in the sources, is using the with statement.
With open as file.
Exactly. The structure automatically takes care of closing the file for you, even if errors occur within the block. It's safer and cleaner.
And finally, what about when things go wrong? Errors.
Error handling is vital for robust programs. Python uses try and except blocks.
How does that work?
You put the code that might cause an error inside the try block. If an error, an exception occurs, the program jumps to the corresponding except block, or you can write code to handle that specific error gracefully, maybe log it or show a message instead of crashing.
You can catch different types of errors.
Yes, you can have except value error, except file not founder, etc., to handle different situations differently. Or a general exception to catch most errors. The sources also mention optional else blocks, run if no error occurs, and finally blocks, always run, simple for cleanup.
Looking back at all these core concepts, variables, types, control flow, functions, OOP, files, errors, how do they fit together to make Python feel easy or fast to develop with?
It's the combination. The simple syntax reduces noise. Dynamic typing cuts down boilerplate. The built-in data structures like lists and dictionaries are intuitive and powerful. Control flow is clear with indentation. OOP is well integrated. And things like with open and try except make common, potentially tricky tasks much simpler and safer. It all contributes to that feeling of getting things done quickly and readably.
Okay, so the core language is solid. But we keep coming back to the libraries. Let's dive deeper into that ecosystem. You mentioned the big names in data science.
Right, pandas for data manipulation is huge. Think of getting data from a CSV file or a database into a clean, usable format. Pandas excels at that. Cleaning, transforming, merging data. It's the workhorse.
And NumPy for the heavy math.
Exactly. Anything involving large arrays, matrices, linear algebra, Fourier transforms. NumPy provides the optimized tools. Many other scientific libraries build directly on top of NumPy's arrays.
Matplotlib for visualization, and SciPy.
SciPy builds on NumPy and provides more high-level scientific and technical computing tools. Things like optimization algorithms, integration, signal processing, statistics functions. It's a broad scientific toolkit.
So for data work, NumPy, Pandas, Matplotlib, and SciPy form a core stack.
A very powerful core stack, yes. Used daily by data scientists everywhere.
Moving to AML again, scikit-learn for general ML.
Yep, described as simple and efficient. It offers a consistent interface to tons of algorithms for classification, regression, clustering, dimensionality reduction, model evaluation. It's often the first library people learn for practical machine learning.
And then TensorFlow, Keras, PyTorch for the deep learning side.
These are the giants for building neural networks. TensorFlow offers a whole platform. Keras provides a high-level, user-friendly API often used with TensorFlow. PyTorch is lauded for its flexibility, particularly in research, great for things like computer vision and NLP.
Python's dominance here really feels like a direct result of these incredibly powerful, specialized libraries existing.
Absolutely. They make extremely complex mathematical operations and model building accessible through relatively simple Python code. Python acts as that perfect high-level interface.
Okay, web development. Flask versus Django.
Flask is the minimalist choice. Gives you the basics of routing web requests, leaves everything else, like database choice, up to you. Easy to start, very flexible.
And Django.
The batteries included approach. Comes with an object relational mapper, or RM for databases, an admin site generator, templating engine, authentication. It aims for rapid development by providing common web components out of the box.
So different philosophies, both popular in Python.
Right. And the sources also mention Pyramid as another flexible option. Python offers choices in the web space.
Automation seems like a natural fit for Python's scripting strengths.
Definitely. Selenium for browser automation is widely used for web testing and scraping. PyAutoY for controlling the desktop GUI is great for automating repetitive user tasks. Python's standard library also has lots of tools for file operations, system interaction, making automation scripts easy to write.
Even cybersecurity tools like Scapy for crafting network packets.
And the requests library for making HTTP calls, often used in security testing and interacting with web APIs.
And Pygame for simple games. It seems the ecosystem covers almost every conceivable domain.
That's the point. Whatever you want to build, there's a high chance a mature Python library or framework exists to give you a massive head start. This ecosystem is a huge driver of Python's adoption and success.
All right, if this sounds compelling, how does someone actually learn Python? What's the path, according to the sources?
The good news is the sources emphasize it's very accessible. Its simplicity plus the sheer volume of learning resources make it a great choice for beginners and experienced programmers alike.
Where should an absolute beginner start?
Interactive websites are highly recommended. The sources mention W3 Schools for clear tutorials and examples you can run in the browser, and SoloLearn, which offers a more gamified, mobile-friendly approach with coding challenges.
What about structured courses?
Plenty of options. Platforms like Coursera and edX host introductory Python courses from universities, often with free audit options. And YouTube is overflowing with free video tutorials. The sources mention channels like Elzero Web School as just one example among many covering all aspects of Python.
Books are still valuable.
For sure. Two popular recommendations from the sources are Automate the Boring Stuff with Python by Al Swigart.
Which focuses on practical automation tasks right away.
Exactly. Great for seeing immediate results. And Python Crash Course by Eric Mathis, which uses a project-based approach you learn by building actual small applications, like a game or a data visualization. And don't forget, the official Python documentation itself has excellent tutorials.
Okay, that covers beginners. What about moving beyond the basics?
The key, according to the sources, is to start building things, real-world projects. Applying what you've learned to create something meaningful is how you truly solidify your skills and encounter new challenges.
And contributing to open source.
A fantastic way to learn advanced techniques, reading code on GitHub, understanding how larger projects are structured, and eventually contributing even small fixes teaches you collaboration, best practices, and deepens your understanding immensely.
The sources also suggest digging into computer science fundamentals.
Yes, learning about algorithms and data structures and how to implement them efficiently in Python. This moves you towards writing more sophisticated and performant code. And then specializing.
Focusing on a specific area like data science, AI, web dev.
Exactly. Pick a domain that interests you and dive deep into the specific libraries and frameworks used there. Pandas and scikit-learn for data science, Django or Flask for web, etc. Mastery comes from specializing within the vast Python ecosystem.
This accessibility in learning seems connected to the large community and ecosystem again.
Absolutely. The abundance of free, high-quality resources lowers the barrier significantly. This brings more people into the community who then contribute back, writing tutorials, answering questions, building libraries, further strengthening the ecosystem. It's that self-reinforcing cycle again, applied to learning.
Okay, so we know it's versatile and relatively easy to learn. Where's Python actually being used out there in the real world? What are some concrete applications the sources highlight?
Its real-world footprint is huge, reflecting that versatility. Data analysis is a massive one. Companies everywhere use Python with Pandas, NumPy, Matplotlib to sift through data, find insights, build reports, visualize trends.
From business intelligence to scientific research.
Exactly. Then there's building websites, specifically the back-end logic, processing user requests, talking to databases, creating APIs for mobile apps to consume, frameworks like Django and Flask power countless web services.
Automation we've touched on, but it's a core application.
Hugely practical. Automating repetitive office tasks, system administration chores, software testing processes. Python scripts save enormous amounts of time and effort in organizations, even used in robotics for controlling hardware.
But AI and machine learning, probably Python's highest profile domain right now.
Undeniably. Training complex models, building recommendation engines, developing image and speech recognition systems, natural language processing. Python, with libraries like TensorFlow, PyTorch, and scikit-learn, is the dominant language driving these innovations.
Can you build regular desktop apps too? Like with windows and buttons?
Yes, although maybe less common than web or data apps. Libraries like Tkinter, which is built in, PyQt, or Kivy allow you to create graphical user interfaces, GUIs, for desktop applications.
And software testing tools are often written in Python.
Widely used. Writing automated test scripts, integrating with CI/CD pipelines, frameworks like PyTest and Unitest are standard tools for ensuring software quality.
The sources also mention scientific computing, command line tools, even blockchain development.
It really pops up everywhere. That glue language idea is important here too. Python is great at connecting different systems and components.
Like linking a web interface to a database and an ML model?
Exactly. Or automating a workflow that uses several different command line tools. Its ability to easily integrate with other technologies, including libraries written in C, C++, is a key reason for its success across so many different real-world applications. It ties things together effectively.
Understanding these diverse uses really highlights why knowing Python is so relevant today. Which brings us to the bottom line for many people, careers. What do the sources say about job prospects for Python skills?
Given its widespread use, the sources confirm that demand for Python expertise is very strong across a range of roles.
Such as, what are the hot jobs?
Data analysts and data scientists are top mentions. These roles involve collecting, cleaning, analyzing data, building models. Python is often the primary tool. Back-end Python developers are needed to build the server side of web applications using frameworks like Django or Flask.
Machine learning engineer seems like a given.
Absolutely. Designing, building, training, and deploying ML models is a high-demand field where Python proficiency is essential. DevOps engineers also rely heavily on Python for scripting automation tasks related to infrastructure and deployment pipelines.
And even cybersecurity.
Yes, cybersecurity specialists use Python for developing security tools, automating analyses, penetration testing tasks. So the demand spans data, web, ML, infrastructure, and security.
Now, salaries. The sources provide some very general estimates, but with big caveats, right?
Huge caveats. It's critical to state these are general indicators from the source material, and real-world salaries vary massively based on experience, role, company, industry, and especially location or country. These are not fixed numbers.
Understood. With that major disclaimer, the general estimates provided in the sources suggest beginners might see ranges around $500 to $1,200 per month, depending heavily on the country.
Intermediate roles are estimated in the $1,500 to $3,000 per month range.
And professional or senior roles are indicated at $4,000 plus per month.
Again, just broad reference points from the sources, not precise figures. They do illustrate a trend of increasing potential with experience, though. The sources also identify some regions with particularly high demand.
Which countries stand out?
Germany, Canada, and the U.S. are specifically cited. Increased demand is also noted in places like India, the UAE, and Morocco.
And metrics like the TIOBE Index topping suggest broad global demand beyond just those.
Exactly. High search volume globally usually correlates with active hiring, especially in tech centers around the world. The demand seems widespread.
And it seems logical that this high demand is directly fueled by Python's critical role in those booming fields like AI, data science, and its core utility in web development and automation.
That's the direct link the sources make. Python skills are needed because the industries and technologies where Python excels are growing rapidly.
Does Python's versatility also mean more career flexibility for individuals?
It does. Proficiency in Python isn't just one skill, it's a toolkit applicable across different domains. Someone skilled in Python could potentially move between roles in data analysis, back-end development, or automation, offering more career pathways.
And while the salary figures were general, the fact that Python is fundamental to specialized high-value fields like AI and ML, that implies significant earning potential for experts, doesn't it? Even if the sources don't give exact numbers for those top roles.
Logically, yes. The sources clearly list roles like machine learning engineer and data scientist as key Python jobs. These are widely known to be highly specialized and often well-compensated positions. So, while the specific numbers aren't detailed, the source material strongly implies that deep expertise in Python, particularly when combined with specialized knowledge in areas like AI, large-scale data, or complex systems, opens doors to careers with very strong financial prospects. Python is the key to entering these lucrative domains.
So bringing it all together, its history, strengths, weaknesses, ecosystem applications, job market. What's the outlook? What does the future hold for Python according to the sources?
The overall picture painted by the sources is very promising. Python's momentum looks set to continue, propelled by its dominance in key areas, ongoing efforts to address its limitations, and its growing role in education.
Continued growth in data analysis and AML seems almost guaranteed.
That's the assessment. Python's simplicity, combined with its incredibly rich libraries, makes it the default choice for so many in these fields. As AI and data science become even more integrated into everything, Python's role as a cornerstone language is likely to strengthen further. The ecosystem creates inertia, new tools, and research often appear in Python first.
And the work on improving speed is ongoing, addressing that main drawback.
Yes, the sources emphasize this. Efforts like the PyPy alternative interpreter, which can offer significant speed boosts, and Python for compiling critical sections to C-like speed show the community is actively tackling the performance issue.
Plus incremental improvements in standard Python itself.
Right. Python versions generally get faster over time. This focus on optimization is important for its long-term health and could expand its use into even more performance-sensitive areas. It shows adaptability.
Its role in education also seems like a strong indicator for the future.
A very strong one. Python is often the first language taught in universities and coding boot camps now because it's relatively easy to pick up. This creates a continuous stream of new developers familiar with Python, feeding the community and ensuring its continued relevance.
So Python's future growth trajectory is closely tied to the expansion of data science and AML.
The sources make that connection explicitly. As these fields boom, Python, as their primary enabling language, is likely to boom alongside them. The switching costs are high, and the ecosystem is deeply entrenched and constantly evolving.
It sounds like a powerful combination. Established dominance in growth areas, active efforts to improve, and a strong educational pipeline.
It creates a reinforcing dynamic that suggests Python's position in the tech landscape is secure and likely to remain prominent for the foreseeable future.
Okay, let's synthesize everything we've covered from this deep dive into our sources. What's the final takeaway? Why should someone listening consider learning Python? What makes it a worthwhile investment?
The conclusion from the sources is pretty clear. Python isn't just another programming language. It's a significant force in modern technology. The key reasons it's worth learning boil down to its unique blend.
Simplicity and power, right?
Exactly. It's simple enough for beginners to grasp quickly, leading to faster development cycles, yet it's powerful enough to build incredibly complex applications, especially with its libraries.
And that amazing versatility across so many high-demand fields.
That's crucial. Proficiency in Python opens doors in data science, AML, web development, automation areas that are defining the future of tech and offer strong career paths.
Plus, the learning curve is made gentler by the huge community and all the accessible resources we discussed.
Absolutely. The sources actually use the word enabler to describe Python. It doesn't just enable you to get a job, it enables you to create, to innovate, to turn ideas into reality across a vast technological spectrum.
So learning Python is framed almost as an investment in your own future capability to build and understand the digital world.
That's the essence of it. An investment that empowers you to participate more fully in shaping technology and gain a deeper insight into the increasingly complex, data-driven systems around us.
That is a powerful way to look at it. So as we wrap up, here's a final thought for you, our listener, to mull over, drawing from everything we've unpacked today.
Given Python's incredible success acting as this glue connecting powerful, low-level components with a simple, productive interface, where else could this unique